Hello everybody. So today we need to review for the final exam. Alright. So I talked to you guys last time a little bit about, I think, an announcement. I said that the last homework assignment, I'm just going to give you credit for it. We just ran out of time at the end of the semester, and that's okay. Good news is we've covered just about everything we need to for a regular Introductory Thermodynamics 1 course. When I first introduced the syllabus, I didn't talk extensively about the learning outcomes with you guys, the course outcomes with you guys. And normally, a lot of times I'll say that, when we've got a comprehensive final in this kind of a course, it probably makes a lot more sense to talk about outcomes at the end of class than it does at the beginning. Well, here we are. We're at the end of the class, so let's talk about the course outcomes. The course outcomes are, upon successful completion of the course, a student should be able to utilize various methods, including tables, graphs, and specific heat content for determining state properties and changes in state properties. Well, we've done that. That was chapter 3 for us, and then we continued on with that throughout then the rest of the semester. Solve problems involving boundary work in compressible systems. That showed up in chapter 4, and that continued into chapter 7. We saw that some more. Simplify general expressions of the first and second laws of thermodynamics to an applicable version for any closed system or steadily flowing control volume. That's chapters 4, 5, this came up in 6, and that's really all of 7. All of that shows up there. And then use first and second laws of thermodynamics in conjunction with other various laws and principles to solve for an unknown value. And that's really what we've built up this entire semester, trying to build up to that point, and we are there. We have achieved that. Exam 3 is kind of a measure of that. The final exam will just kind of be a reiteration of that. So those are the course objectives. There's this last course objective. Again, we ran out of time this semester, but the idea of utilizing a simple ideal model for gas or vapor power cycles. And in chapter 6, we do cover that to a small extent. The Carnot cycle is an ideal cycle. And we did utilize that in vapor cycles for refrigerators and steam engines using R134 and using water going through a vapor liquid phase change throughout the cycle. So in theory, we've covered that objective. Typically, with a little more time, we would have covered that more in depth in chapter 9, talking about some gas cycles, the Otto cycle specifically, and or the Rankine cycle. And again, we just simply ran out of time this semester, and that's okay. So we've hit on this 5th one. We've really covered extensively these first 4, and that will be more than sufficient to get us going in the introductory thermo course. Okay? So with that in mind then, let us review for the final. Now, again, in the learning outcomes we talked about, you need to be able to identify properties of substances. Okay. So when we talk about properties of substances, if we have water or R134A, those are the two substances our textbook has tables for. You'll find ammonia, propane, maybe R410, refrigerant 410. You'll find some other substances in other textbooks. Our text only has these two substances because if you can use the property tables for these two substances, you can use the property tables for any substances, honestly. So if I've got water R134, the general rule is to use tables. Do not treat R134 as an ideal gas, period. Right? It's very rare we will deal with R134 where it stays in the vapor phase and close enough to the gaseous phase that ideal gas laws are reasonable estimates. Just don't do it. If it's water, maybe you can use it as an ideal gas, but I really recommend against it because your tables are so much better and much more accurate and precise. Use tables. To use the tables, you need two properties. You need to know two properties. There's two common categories this shows up as. We talked about this back in chapter 3. This has not changed. Either given P or T, right? Given P or T, and then down here on the x-axis I could be given V, U, H, or S. Any of those four properties. My graph's going to look something like this. It's going to change a little shape for the S, but the general idea is the same. Everything to the left of this dome is liquid. Everything to the right of this dome is what we call superheated vapor. And anything in between is a mixture. Saturated mixture. If it's on the vapor side of the dome, it's saturated vapor. If it's on the liquid side of the dome, it's saturated liquid. Saturated just means it's boiling. It's full of energy. It's saturated with energy. We add any more energy, some of that liquid will go through a phase change. Or if we remove any energy, some of the vapor will go back to the liquid state. Okay. Right. The other scenario, the other main scenario we might encounter is, this is where I'm given P or T, but if I'm given P and T, then my graph looks like this, and you've got basically this, you can draw this arbitrary curve, and everything to the left of the curve is liquid, everything to the right of the curve is vapor. Given a pressure value, go look up, right, so P given, go look up your T-sat, your saturated temperature, the boiling temperature, if you will, and determine whether your temperature puts you in the vapor or the liquid region, and that will tell you your phase. If I'm in the vapor region, this is the superheated vapor region, go to the superheated tables. That's simple. Okay? If I find I have a liquid, just use the temperature and approximate it as saturated liquid at the given temperature, and that will get you really close. Right? Right. We talked about interpolation. We talked about so there's a couple of in between there. Right. We talked about interpolations. We also talked about saturated mixture. Right. We talked about a saturated mixture. We said that X, which is what we call the quality, this represents the portion in the vapor phase. So again, what do we do if we're in the dome? Because you're going to go at your given value, you're going to go look up the value for saturated liquid, and go look up the value for saturated vapor, the F and G values, for whichever of these four that you have. If you have a value that's between these two, that puts you in the saturated mixture region. Part is in the vapor phase, part is in the liquid phase. You need to determine how much is in the vapor phase. So if you compute this quantity, and this could be U, H, S, or the specific volume V, compute this quantity, and then you can set it equal to all of the other quantities. So compute it for one of these four properties. You compute X, then you can use X to compute any of the four properties. X is going to be a value always between 1 and 0. It can be 1. If it's 1, that means it's a saturated vapor. Notice if I plug in Vg in here, I get 1. That's a saturated vapor, 100% in the vapor phase. If I plug in Vf, if it's a saturated liquid, and I plug in Vf here, I get 0. A quality or an X value of 0 tells me I've got 100% in the liquid phase or 0% in the vapor phase. And that's a good stopping point.